Hi everybody, welcome to another video in Calculus 2. We go to the last chapter, Parametric and Polar Curves. First, Parametric Equation. You should learn most of this back in pre-calculus, but now we just do pretty much the same thing, Parametric Equation, Polar Equation, but now we add the calculus part to it. But first, Parametric Equation. Shall we say parametric equation of x and y in terms of t, usually t represent time. So we can say parametric equation is x is a function of t and y is a function of t, and t is usually time. And then the parametric curve will be the set of all the xy, or in this form. And that is called the parametric curve. Right. So now, first let's graph and analyze this parametric equation. So we're going to graph that. It should be easy. Just make a little table x, y for x and y. T go from 0 to 4. And then x equal to 2t, and y equal to 1/2 t squared minus 4. Right. So now if x equal to 2t, we just multiply all of this by 2. 0, 2, 4, 6, 8. Easy enough. Now put 0 in here, we have negative 4. Put 1 in there, that is half minus 4, so negative 3.5 and so on. We actually can just use the calculator to do this. So hit y equal 2. That's not going to work. Actually, I did this for another example earlier. Right. So if we want this to graph in parametric form, hit mode. Make sure this is in the parametric form. Alright, the second one. Then we can enter the function y equal to x equal to 2t and y equal to I just say 0.5 t squared minus 4. And when I hit second table, I should have the table. I'll just copy those values. 0.5 and then 4, right? So 0, negative 4, 2 and negative 3/5, 4 and negative 2, 6 and 0.5, and 8. Oh, that's 6, so it should be here. Sorry, 8 is going to be 4. And so we have the curve. If we hit graph, right, we actually need to change. I say we go from 0 to 4. And from 0 to 4, so the length is 4. I divide by 100, so it will graph 100 points. Let's see. Right, so it go like that, because exactly what we have here. So the difference between the graph of the curve in this the parametric equation is that in this curve we have the direction, so it go that way and have the starting point and the end point. Right. So it's easy to graph. Now if we want to actually see what is the graph of this, there's another way to do this. We can from here x equal to 2t. So we can show for t x equal to 2t, so t equal x over 2, and I will substitute this into this t. So y will be equal to 1/2 x over 2 square minus 4. So multiply that, we have y equal to 1 over 8 x squared minus 4. Now let's change back quickly to function and then graph this 1 over 8 x squared minus 4. Right. If you see the portion of it from here to there, so it's the same. But the difference between this function and that, this function and the parametric equation, is that in here we specify t is go from 0 to 4. Now, we can also write that. Remember, in parametric equation, in this example, we have this. But t is equal x over 2. So normally we substitute in there for the function. We substitute in here for t as well. So in that case, we will have 0 less than equal to x over 2 less than equal to 4. Multiply 2 on both sides, we have x between 0 and 8. So if we want to graph, we can say x between 0 and 8. So that equation will be similar to that, represented by this. However, we still not the same. In the parametric equation, we know the direction too. But actually, yeah, from here. But in this form, if we want to go backward, we won't be able to do that. In the parametric equation, that's easier to say how fast it's going and what direction it goes. But if we want to, we can convert the parametric equation into a function or the equation of x and y, and we can graph that. But in parametric equation, it is easier to see where the pocket graph goes. Right. Now, so certainly we can graph it. We can convert to equation of x and y. But note that in the parametric equation, the direction and the end in the initial point. So more information in the parametric equation, if you will. Alright, now try to analyze and graph this. Because to graph is simple, but what I want to do first is try to convert it into the equation of x and y, something similar to this. Right. If I want to do similar like this, I can solve for t. However, that will involve cosine inverse, and that I don't want to deal with. However, what I see is this one has cosine, this one has sine. Cosine square plus sine square is 1. So I will utilize that Pythagorean identity. Right, so start with x equal to 4 cosine of 2 pi t. Let's solve for cosine of 2 pi t is equal to x over 4. Square both sides. X square over 4 square. I'm just going to keep 4 square for now. And then do the same thing for y. So for sine first. And then square both sides. And then I can add side by side. We have cosine square plus sine square on that side. Pythagorean identity cosine square plus sine square. Notice that the argument here have to be the same. So in that case, we have 1 on this side, and the other side we have x square over 4 square plus y square equal to over 4 square. Multiply both sides by 4 square, we have x square multiplied 16 of 4 square on both sides. We should have 4 square equal to x square plus y square. Now, this is the equation of a circle, center 0, 0, radius 4. So this equation is a circle, center at 0, 0, radius 4. I have a compass, but the scale is a little off here, so I kind of have to draw it by hand. Yeah, because the scale of x and y are not the same, so using compass doesn't help here. Anyway, so that's circle. However, as I said, this equation and that equation, there are a lot of information that is missing here. So first of all, we don't know where the direction goes. So let's graph this first and see what happens. Mode change to parametric form and enter equation 4 cosine 2 pi t, then 4 sine of 2 pi t, right, graph. It is still running, but because that's not what we want. We want t only from 0 to 1. So 0 to 1. And the t step, we want from 0 to 1. So the length is 1. We divide this by 100. So pretty much we will graph 100 point. And see, it is a circle. The circle that starts here and go counterclockwise. And only that, from 0 to 1, it will complete 1 revolution. So, before we go to the circle, let's just look at this example. What can we do? So, when we have the parametric equation, we can eliminate the parameter, eliminate t, and end up with the equation of x and y. Either that or that. So there are two ways to do that. One is we solve for t directly, and then substitute into the other equation. Another way to do this is using the Pythagorean identity, cosine square plus sine square equal to 1. So those are the two ways to eliminate the parameter. So in that case, we have the equation and then we can graph. Right, so that's the first part of it. Now if we focus more on the circle in particular, and in general the graph, there will be a lot of factors that including to this. So when we talk about a curve, we have to know where start, where it ends. So the first one, where start, where it ends. Second, how fast does it goes, and then third, what direction does it goes. So now again, if we have a circle, it can go extremely fast or it can go very slow, clockwise or counterclockwise. It can start here or it can start here. So there are three factors: the speed, the orientation, clockwise or counterclockwise, and where it starts. So now if we focus on the circle, we will have this general form, parametric form of a circle. In this case, we have the center at the point x0, y0. the circle is traversed 2 pi over b time unit. So if we want this to go 1 revolution, 2 pi over b, absolute value of b will give us the time that it travel 1 complete revolution. Varying b will vary the speed at which the circle with the curve unfold. By the way, if we want an ellipse instead of a circle, we will change the coefficient, those a and a, to be different numbers. If we put that 2, then we elongated it and make it an ellipse. But that's another example. And then b will vary the speed. And if it's positive, counterclockwise, negative, clockwise. So certainly we can choose b to be positive or negative to control the orientation, clockwise or counterclockwise. And then we change b to be big or small, so to control the speed. What we don't have here is where it starts and where it ends. In that case, we have to choose that. When we see the example. Anyway, so we will have an example like that. But first, so that is a way we parameterize a circle. Now, if we want to parameterize a line, it will be in this form. This is a line. And if we want the whole line, we can say from negative infinity to infinity. And x0 and y0 is just a point on the line. Right, next, describe the curve when b equal to 0 and describe the curve when a equal to 0. Now let's look at this equation. If we have x equal to x0 plus at and y equal y0 plus bt, when b equal to 0, we have x equal x0 plus at and b 0, meaning y equal to constant. If y is constant, they have the same y values, so it is horizontal line. And if a equal to 0, x equal to x0, and y equal to y0 plus bt, x equal to a constant, so it is a vertical line. They have the constant x values, so vertical line. Right, we will do the line and the curve in a minute. But now let's the line and the circle in a minute. Now focus on the general curve. So earlier we have equation in parametric form, convert that into the what we call the rectangular equation. Now we do that in reverse. Let's say if we have this, how do we write this in terms of function of t? Right. If we have the function y equal to this, it will be very easy. We just say, why don't we let x equal to t? If x equal to t, we have y as a function of x is a function of t. Right. First, let x equal to t on this example. So we're going to try to write this as the parametric equation, and that's what we call that parameterize. It might spell parameterize. Both of them mean the same thing. So we write that this equation in terms of the function of t, or parametric equation. Right. If we choose x to be t, then x between negative 1 and 3, so we also have the same thing. Right, and then y equal to 9 minus x squared will be equal to 9 minus t squared. So we have x equal to t, y equal to 9 minus 9t squared, and then t between -1 and 3. Right. So parameterize it, turn this equation into the parametric equation. Right. Simple enough. Next, the complete curve x equal to this. Now this one we have x as a function of y instead of y as a function of x. So if it is like this, we should choose let y be t. In this case, actually we don't have the limit for y or x here, so we're just going to leave at that. But we have x equal to y minus 5 square plus square root of y, but y is equal to t, so this equal to t minus 5 square root of t, right? And then so we can say x equal to that, and y equal to t, and this is no domain for t, but we have parametric equation x and y in terms of t. Right, simple enough. Next we want a linear path that connect -2 to 0 to 0 to 3 in that order, where the parameters go from 0 to 2. So in that case we need two functions, x and y in terms of t, right? Now let's look at the x values first. -2 to 0, right? So we will make the table. So we try to find the function of x in terms of t and the function of y in terms of t. Right. When t equal to 0, at t equal to 0, we go factory from this point to that point. So t go from 0 to 2, x go from -2 to 0. So we need to find x as a function of t. Right. Right. So t go from 0 to 2, x go from -2 to 0. Right. Now what we have here is most important, and this is a linear path. So this is equation of line. So this should be simple. Equation of line. First we find the slope. Usually y2 minus y1 over x2 minus x1. So in this particular, the slope, instead of y, we're going to use x. So we go from -2 to 0. So we y2. So in this case, we have 0 minus -2 over 2 minus 0. So that gives us 1, right? 2 over 2 is 1. So equation of a line, the slope is equal to that. And then next the equation is going to be y equal to mx plus b. But in this case, we're going to use x equal to mt plus b instead. So instead of x and y, we go to t and x. Right. So we have the equation x equal to mt plus b instead. The slope is 1. So if x equal to t plus b, and then when t equal to 0, x equal to -2, t equal to 0, x equal to -2. So from here we can see b is negative 2. So I have negative 2 and the slope is 1. So the equation is x equal to mt plus b. So x equal to mt 1 times t minus 2. Right. Then we can check. If we put 0 in for t, we have negative 2. If we put 2 in for t, we have 0. Right. So if it is a line, find the slope and then the equation. Right. Now we do the same thing. T go from 0 to 2 again, but y values go from 0 to 3, and try to find the function. First the slope, y2 3 minus y1 over t2 over t1, t2 minus t1. So that gives us 3/2. So find the slope. And next y equal to mt plus b. The slope is 3/2. And when t equal to 0, y equal to 0, so b is 0. So at b equal to 0 and the slope is equal to 3/2, we will put in the equation of the line here. So we have y equal to 3/2 t. So x and y along with the domain for t. So let's try if it works. T minus 2 and 3 over 2 times t. Make sure that we have to change the window from 0 to 2. I'm going to zoom in. Actually have to zoom out. Right. And then zoom box. So pretty much just zoom that windows, and as you see it go from negative 2 0 to 0 and 3, so go in that. So because we know this is a line, so the equation is of a line in general is that. So we find the slope and find the y-intercept. And in this case we want specifically so actually let's just write the answer here. X equal to t minus 2, y equal to 3/2 t, and t between 2 less than 2 and greater than 0. So this is the parametric equation. It's easy to know that it is it is a line. Right. We have a definition here. The direction of the parametric curve as the parameter increase is forward or positive orientation. So if t go from 0 to 2, we have the forward or the positive orientation. If we want it to go backward, we have to change t to negative t and it go backward. We'll do that later. Now, before we do more parameterization, now just focus on briefly on the calculus part of it, just the derivative. We will study a little more of this in the next sections. But for now, basic. I say if we have the parametric equation x and y as a function of t, and both of them are differentiable, then derivative of y with respect to x is given in that form. Well, actually, when we write out, actually it makes perfect sense. Let me say, let's see, dy over dx. I can do it like this. If we write this, but in the reciprocal, right? Because if the dt cancel out, we have dy over dx. Although we technically will not cancel out the dt, but in terms of notation, it works just like that. And then, of course, multiply is divide the reciprocal. And this is, of course, y is a function of t, so h of t, so this is derivative with respect to t. So that's why we have that. So simple enough. Right? Like I said, there will be more example of this. Now let's find dy over dx of the following curve. Determine the point, if any, at which the curve has a horizontal or vertical tangent line. Right. If x equal to t, y equal to 2 square of t, what is dy over dt? I mean dy over dx. We're trying to find the derivative. Of course, we can also write as the function of y in terms of t and the function of x in terms of t, like that. I think sometimes it's more convenient to write in that form. Yeah, because sometimes we might not have g and h. Perfectly fine. Right, anyway, dy over dx. So derivative will be derivative of y with respect to t over derivative of x with respect to t, if we have t in the equation. So it's simple enough. Derivative of t over derivative of 2 square root of t. Square root of t, I can say t to the 1/2. Take derivative. Derivative of t is 1. Derivative of that 2, 1/2. And derivative of t to and then t to negative 1/2. This will be easy. So 1 over 2 and 2 cancel out, t to negative 1/2. And then at the bottom we move that to the top, become t to the 1/2, or just square root of t. Right. Next, determine the point at which the curve has the horizontal and the vertical tangent line. And actually, sorry, I did this completely wrong. Y prime, I should have this. And the formula is perfectly fine. I just do that. Right, don't make this mistake. First, if we want y is 2 square root of t, that derivative of y over derivative of x. So make sure you write out what is x and what is y correctly. Derivative of this is 2 1/2 t to negative 1/2. Derivative of t is 1. So cancel out, we have t to negative 1/2. I'll move this down, we have 1 over t to the 1/2. So which is equal to 1 over square root of t. So we have dy over dt, dy over dx is 1 over square root of t. Right. Make sure we know which one's y, which one's is x, and do that accordingly. Derivative of y over derivative of x with respect to t. Right. Now for this, which one of t will make this one horizontal, which one of this will make this vertical. By the way, if this is the case, horizontal tangent line is where the slope equal to 0. If this one horizontal, that means the slope is equal to 0, and this function cannot be equal to 0, so that will be none. 1 over square root of t cannot equal to 0, because we cannot choose the t to make this equal to 0. We have 1 on top, cannot be equal to 0. Next, if we want to be vertical tangent line, derivative is undefined. If the derivative is undefined, so 1 over square root of t is undefined, where the denominator equal to 0. If we divide by 0, it's undefined. So vertical at t equal to 0, of course we have that vertical tangent line, and on the tangent line after that, it will not be horizontal. It will be horizontal when t approaching to infinity. In this case, that will go to 0. Yeah, t has to go to infinity for this to be 0. Right, so it's just flat out, and when it approaches to infinity, it will be horizontal. Right, so that's what we have. Right. We do the same thing. We have an ellipse here, and we're trying to find the derivative. Derivative of y with respect to t, derivative of x with respect to t. Right. So I think it's useful we just write out y is 16 sine t and 4 cosine t for x. Derivative of 16 sine t is 16 cosine, and derivative of 4 cosine t is negative 4 sine t. So we will have negative 4 cosine over sine will be cotangent of t. Right. And then it's easy to see where cotangent equal to 0, we have the horizontal tangent line, and where cotangent equal to when cotangent is undefined, we have the vertical tangent line. So horizontal tangent where derivative equal to 0. And we have -4 cotangent t equal to 0. That's the same thing as cotangent equal to 0. The -4 doesn't really do much. And then here we can cotangent, right cotangent is cosine over sine. Cosine over sine. If this is 0, then cosine is equal to 0. And cosine equal to 0, we have pi t equal to pi over 2 or 3 pi over 2. So horizontal tangent line there. Vertical tangent line is where derivative is undefined. And then the derivative is this, or we can just say it for cotangent is undefined. And that gives us -4 cosine over sine is undefined. This one's undefined where the denominator equal to 0. So we have sine t equal to 0. So t equal to 0 and pi. So we have vertical tangent here and here. Right. So it's simple enough for the derivative. Later on we'll do a lot more of this in the derivative. But that's the basic example here. So if we have x and y function of t, then dy over dx is derivative of y with respect to t over derivative of x with respect to t. Right, we'll do more of that later. But for now, we have more examples for parameterize a curve. So find a parametric description of a line segment of that. So in this case, we didn't say t have to go from where to where. It doesn't matter. And it also did not say in what direction it goes. So, but actually it does. It goes from 0, 0 to 2 and 8. So we do two things here. We make a table of t and x. Let's choose t go from 0 to 1. That's standard. And x go from 0 to 2. We will try to find the equation. Now that's easy. It looks like x equal to 2t, right? But let's just do the slope, the change in y over change in x. And then x equal to mt plus b t plus b because m is equal to 2. And then we have 0, 0. When t equal to 0, x equal to 0. So b is equal to 0. Now b equal to 0 and m equal to 2. So x equal to mt plus b, which is 0. So So if x equal to 2t. Now we do the same thing. For y. Let's say go from 0 to 1. And then y go from 0 to 8. First the slope, the change in y over the change in t. So it's just 8. And then y equal mt plus b. M is 8. And once again, when t equal to 0, y equal to 0. So in this case, b equal to 0. So we have the equation y equal to m, which is 8, times t plus b is 0, so y equal to 8t. So bottom line is we have the equation x equal to 2t, y equal to 8t, and t go from 0 to 1. So once again, that's how we parameterize a straight line. Right, now, how about we do that for a circle? Find a parametric equation for the circle center at the origin, and the radius 12 generate clockwise, and initial point 0 and 12. So there's quite a few things here. Right. So we do know that this is clockwise, so that is important. The radius is 12, also important. Center at the origin, also important. Initial point. So there are a lot of things to worry about. But in terms of the equation of the circle, though, that is the equation of the circle. So let's just write x equal to x naught plus a cosine bt, y equal y naught plus a sine bt. Right. Now what we know? The center at the origin. So that means x naught and meaning 0 and 0. So that's 0 for x, that's 0 for y naught. Right, so we know x naught, y naught. The radius equal to 12. That means 12 is here. And here. Right? Clockwise, b is negative. B is positive. Counterclockwise, b is negative. Clockwise. Now put all of those together. What do we have? X equal to 0 plus 12 cosine of bt. Just note that b is negative. And then y equal to y naught is 0, 12 sine of bt. Right. Now, one thing we did not know is how fast it goes. It did not tell the interval, right? But we do know that it have to start from 0 and 12. Right? Excuse me. Right. So it's this we know from 0 to 12. So what can we see here? Right. By the way, just write down the fact that the circle will traverse a whole circle 2 pi over b times unit. So if we want to say, let's say we want to choose an interval to be 1, then that will be different. The interval to be 2, find the interval of t, then that will be different. Since this one did not specify, we can choose b to be either 1 or -1. Right. It did not specify here. So in this case, let's just choose b equal to -1. If we want to speed this up, we will do differently. But for now, it did not say anything about the speed. So x equal to 12 cosine of -b, which is b is -1, so -t, y is 12 sine of -t. Right, now the initial point. We don't know where start yet, but we have x equal to 12 cosine of -t and x equal to 0. Now x equal to 12 -t, cosine equal to 0, where that -t is equal to pi over 2. So we certainly can write like that. Just look for something. Right. So t equal to -pi over 2. And then when t equal to -pi over 2, we put in here sine of pi over 2. And if we put -pi over 2 in here, negative pi over 2. So we just need to make sure that it check out with this. T equal to -pi over 2. We have y equal to 12 sine pi over 2 is 1, so this equal to 12. That check because we have the point 0 and 12. So when t equal to -pi over 2, that certainly works. Right, now, so bottom line is we will have x equal to 12 cosine of -t, y equal to 12 sine of -t, and t, we start from -pi over 2. Right, it did not say that parameterize that to go one complete revolution, but we still can do that too. Right. Now let's zoom number 6. Now enter the equation. By the way, we certainly can change this. X equal to 12 cosine of -t. Y is 12. Wait. That is negative. So that doesn't work, right? Because sine of, we can see in here, let's graph. By the way, let's go from negative pi over 2 . That's 2 pi, so it's fine, but right. So let's see. Let's graph very slow. So it's the start from that point, and it go here. Oh, never mind, negative and negative. So that check. Sorry, that works. So that's perfectly fine here. Yeah, I forgot there's 2 negative signs. So yes, that check. So this equation is correct. Right? Right. So make sure that we choose form for x and then make sure that also works. Both of them work. So it's negative pi over 2. Right. Now, important thing is, what if we only want to go 1 revolution and we don't want to go past that? So yeah, so make sure always check for both x and y. Make sure that that's where we start. So yeah, we have that. I forgot 2 negative signs earlier. Sorry. Anyway, so we have that equation, which is good. By the way, the question is done. Now we just want to have the upper bound, so it is exactly 1 revolution. Right. Now, what is the? We have cosine and sine like that. By the way, if we want to, we can always say cosine is even. So cosine is even. I will write here. Cosine is even. Cosine of negative x is equal to cosine of x. So cosine of positive or negative is still the same thing. And sine is odd. So sine of negative is negative sine. And we know t is greater than negative pi over 2. Right, so that is even. I'm just going to write somewhere. Sine of negative is negative sine. Right. Now, how fast it goes though. Now this is sine, cosine of t and sine of t. Now if we go back way back to trigonometry, we talk about the period. A period of cosine and sine typical is 2t, I mean 2 pi. So we just find the period of this, meaning that after a period it will repeat, go back to the original point. So the period of sine cosine here is 2 pi. So within the interval of 2 pi, it will travel 1 complete revolution. So what we do here is we just say from negative pi over 2 to negative pi over 2. We're going to add 2 pi to it. That will get 1 complete revolution. If we have 2t here, the period of that is going to be a pi, so we're going to add a pi to it. So the answer is x equal to 12 cosine t y equal to negative 12 sine t. 1 revolution, we start from negative pi over 2 to 3 pi over 2. Yeah, so that is the answer for 1 complete revolution. To recap, we start with this: the center, the radius A and then we determine B. If B is positive, counterclockwise. If B is negative, clockwise. And we don't know how fast it goes. If in this case we say, let's say the interval only 1, then we have to do this and find out what is the period. For example, if I said, what if the interval is only 1, then we have to choose B so that the period of that is equal to the same as the length of the interval. In this case, the period is equal to 2 pi, so I'm just going to add 2 pi to it. If we want to go, the period is only a pi, then we're going to have 2 in here. If we have, for example, if we have bt sine of bt, if we have this equation, then the period is equal to 2 pi divided by absolute value of b. So that is a period, so 1 cycle of it. So in this case, because we choose 1, so the period is 2 pi, so that's what we have. So if we want to graph this perfectly, we will change the windows. That goes from 3 pi over 2. And then when we graph, we start from there. And when it stops here, this one will stop. See? So that completes 1 revolution. Start from that point and go go clockwise, exactly like what we have here. All right. Once again, if we want to go twice as fast, put the 2 in here. If we want to go slower, put some smaller than 1. The 2 pi here is the period of that function. Right. Just make sure when we start, have to check both of them to make sure that we actually start at that point. Right. So that is parameterize a circle on ellipse if we change some numbers here. Right. Write the equation of x and y that corresponding to this parametric equation. Now after that, when we have, it will be easy. We have equation like this. So we can choose either x or y to be t. Now if I choose this and it's trying to solve for t, will be x plus 3. And we just substitute that in here. So y equal to x plus 3 square. Right? And we just need to specify the domain of the variable x or even y still work. Anyway, t is x plus 3, so I'm going to put x plus 3 in here. Put in there as well. I subtract 3 everywhere. Negative 5 x and 0. So that's all, right? If we have equation of x and y, that would be easy. So for x, so for t, and then we substitute in there. In that case, we eliminate the parameter t. Right. Now, so that's pretty much this section. So in this section, we only do parameterization, and then one way we are given the equation of t, we try to eliminate that, have x and y, or we have the equation of x and y, eliminate t, or we have the equation of x and y, we introduce t into it. So pretty much convert parametric equation into the equation of x and y. Right, and also we can parameterize a line segment like that, and parameterize a curve, a circle using this equation. Initial point x naught and y naught give us the center, a give us the radius, b give us how fast it goes, and clockwise or counterclockwise. So make sure that if we know the initial point, we have to check to make sure that the initial point actually works. And also how fast it goes around the circle will be given by the period. The period for the problem is 2 pi, so which means within one period it will travel one complete revolution. So we just add 2 pi to it, we'll get one complete revolution. Yeah. If this is something else, then the period is 2 pi divided by absolute value of b, and that gives us how fast the time it takes to go one complete revolution. Anyway, so that's for the circle. And then for any other equation, it will be easy. Whether we have y and x, we introduce t, or whether we have x as a function of t, y as a function of t, and we eliminate the parameter t, those should be easy. Anyway, so this should actually just kind of like the review what we have in pre-calculus. The only new thing here is the derivative in the parametric equation, just the derivative of y over derivative of x with respect to t, and that should be it. So I'll stop the section here. See you in another video in Calculus 2. Thank you for watching.